Welcome class to Chapter 12 on one-way analysis of variance, also called Anova. So the chapter gives the example of a research question. Which text format would be most preferable to students? Excuse me, the traditional paper text, standard electronic text, or interactive electronic text. And they collect satisfaction ratings from the group and they compare the mean ratings across the text formats to see which one they like the best. And so Anova, no different than a t-test in the sense, and a lot of the other inferential tests that we've studied, in the sense that you're comparing differences, right? Comparing differences with error over estimated standard error. It's just calculated a little bit differently. But I just want to remind you that the Anova is really building off of all the stuff that you learned earlier. Okay? So we're comparing differences and seeing how much of a shocking difference that is so that we can reject the null hypothesis, because it just, that data looks, makes our null look ridiculous, right? Okay, so in the Anova though, we have more than 2 independent samples. So that's the key there. Analysis of variance. Anova is a common inferential test used by researchers to test their hypothesis in psychology. It can be used with both between subjects and within subjects designs. You can have more than one independent variable also. This chapter focuses on between subjects designs with one independent variable. The other 2 chapters talk about this stuff that I just mentioned, but you don't have to learn that stuff. It's a little more complex, and so in the interest of the 16 weeks, I decided to cut those 2 out. And you could read about those though and learn about them, but in any case, we're going to jump on to correlations after this. Between subjects design with 3 or more groups, that's what we're studying right now, right? Instead of the 2 groups, comparing 2 groups, we now have 3 or more groups. When we compare scores across 3 or more groups, we're using a between subjects design. The individuals in the sample either come from different populations, right? Or the individuals in the sample are randomly assigned to different conditions. They're exposed to different conditions within the study. As always, the goal in both cases is for the groups created in the study to represent the population that it came from, right? And the null hypothesis, all the population means are equal to each other, okay? And then the alternative hypothesis, the book points out that there can be multiple possibilities, right? One population mean is greater than the other or lesser than the other, right? Or all population means are different from one another, or at least one of the populations will be different from the other, and that's the alternative hypothesis that they chose in the example with the electronic text, or type of text. Anova, always a one-tailed test, since the values always positive due to using the variance. Remember the variance back when we studied that, just a little variation of the standard deviation, right? Standard deviation is the square root of the variance, and so therefore the variance is the standard deviation squared. We cannot simply use the difference between sample means and the top portion of our ratio as we did in our t-test, right? Because we have multiple sample means, and we'll have, that's what it says right here, we'll have multiple mean differences to consider 3 or more groups to compare. So we use the F ratio to compare the mean differences. And there's 2 terms here, the between groups variance and the within groups variance, which you'll see is basically the F ratio is 1 over the other. The between groups variance is the average square difference between the sample means and the overall grand mean. So it's really all the differences of the different samples, right, from the overall grand mean, which is basically going to show you treatment effect, right, plus error. And then the within groups variance is basically just like your estimated standard error. It's the average square difference between the scores in each group and group mean, okay? So then notice that this is the between groups variance. It's the variance of how each group, between each group, okay? So how they differ between each group. And then the within groups variance, just think of it as the variance within each of the separate groups. Okay, so estimated standard error within those groups pooled together. And I pretty much just said a lot of this stuff, but the F ratio is treatment effect plus error over error. So essentially when you cancel those out, you get to find treatment effect, which is super cool, right? And you get to use this with 3 or more scores that you're comparing, means that you're comparing. The F ratio is basically the between groups variance, which is treatment effect plus error over within groups variance. And the total variance of the total package of kind of what you're studying, what you're looking at, is of course the between groups variance plus the within groups variance. F distribution, we're just talking about the way that it's shaped. It's similar to the distribution of t-scores, except because we're using variance terms, F can never be less than 0. F will not equal 0 unless there's absolutely no variability in the data, and that doesn't occur in real life. So essentially F ratio will equal 1.0 if there is no effect of the treatment or independent variable. So think of 1.0 as 0. But it's not, right? So starting point 1.0, that's what that basically this slide means. And as you can kind of see right here, starting point right here, F distribution is positively skewed. Remember, the tail is at the higher end of the values right here, critical region there. But as you can see right here, it's positively skewed, and F starts at 1.0, and that's because we use the variance instead of standard deviation. F distribution has 2 degrees of freedom terms that you'll want to know. And basically, remember, just start figuring out the equation and then what to plug in where in the equation. Have your notes kind of lined out so you can really easily find different terms that you're asked for on the quiz or exam. For example, the between groups degrees of freedom is 1 less than the number of groups in the study. So let's say you had 3 different groups, then you would have 3 minus 1, for example, where A is the number of groups. And then the within groups degrees of freedom is the number of groups times the number of subjects in each group minus 1. So in the previous example, if you had 3 groups, and then I think the book has n equals 30, then you can multiply, you would have 3 minus 1 here, which would be 2, and, or excuse me, 30 minus 1, which would be 29 times 3, and I think they give that as 87, I want to say. Calculating the F score in Anova. So basically, let's go through our steps of hypotheses testing, which is no different than the t-tests and the other ones, right? But it's just a different equation. Null hypothesis is there's no difference, right, in the scores. Population means for using paper, standard electronic, interactive electronic texts are equal. So the mean of each of those is equal, right? No difference between those. But you're probably hypothesizing that, you know, these electronic ones are going to be better than the paper one is what you're kind of thinking. And, you know, you're selling, you know, mozzarella, and do you want to decide to change and sell string cheese? Or you're using paper tests and you're wanting to know, are these different versions of text better for your students to learn? So, of course, you're going to test that because you don't want to, you know, go out and buy a bunch of these electronic texts if they're just going to flop and be the same or worse than learning in the paper, right? So what's your alternative hypothesis? That you want to hopefully make this null look, ridiculous and shameful that you held on to these paper texts for so long. You know, you curmudgeon, you Luddite, you're holding on to these old technologies, these old teachers, right, that just bore you. Oh, I'm falling asleep while I'm listening to him. Oh, hopefully that's not me right now. And alternative hypothesis is at least one population mean is different from the rest of the text formats, populations. As is typical, we'll set our alpha level to 0.05. You can also do it at 0.01, but 0.05 is where typical. And then remember mise en place, which is get what you need for the equation in front of you. Write it all out. Take a deep breath. You can plug in stuff. You can use your PEMDAS, right, for the math, and you can figure this all out. You can also plug it in SPSS and get the answer too. But in any case, here we go. So you got the mean of the paper is 4.17. Mean of the standard electronic is 5.33. In terms of the ratings, favorability ratings, and the interactive electronic 7.83. So just at face value, which one looks better? Of course, the interactive electronic is better. Interactive, I almost had nuclear option. Interactive electronic 7.83, much better than the other two, and this one's better, the standard electronic, than the paper. And we're wondering, this one probably is a significant difference, right? Just from the data you've seen. You have to look at the standard deviations, of course. It looks like it's better, though. And this one is like, all right, I don't know, maybe not. Who knows? We'll take a look at it. And then you have, so those are the means of ratings for each group. And then you have the this X with a bar with a sub total, which is another word for the grand mean, which you need to find. And that's adding these all up and dividing, and then that's your grand mean. Okay. And then you have, remember the sum of squares? We learned that when we were learning about variance, right? Just another, way to talk about standard deviation, right? Or it's an element of standard deviation, right? Variance, just an alternative way of, remember that, of standard deviation. So we're really using these terms to find our estimated standard error, right? No different than learning about the t-test. Just we're using just a little different values. Remember that the variance and standard deviation are just alternatively very similar, except the standard deviation, right, is the square root of the variance. And so anyway, they give you these values. You don't have to figure them out, which is kind of nice for each group. And for each group, the paper sum of squares is 53. Standard electronic 75, and the sum of squares for interactive electronic is also 75. So the variability there is the same. And so step 4, we're going to calculate the statistics. So we have our data and collect our sample data, it's all ready. So we have this in front of us written out, right? And now we're going to take a look at the actual F equation, and then we'll break each one of these up and show you how to figure those out, given that you already have that other information that you can just plug into each of these formulas right here. But you'll see the F ratio is the between group variance, how much each group varies, right, between one another, which is what you're wanting to find, right? And they look like they varied in terms of the mean compared to the overall grand mean, right? And so looking pretty good right there for that top value. And the top value you want is high, right? And the bottom value you want is low. And basically you want high variability between your groups, right? So that you can say, whoa, that's shocking, and this looks like a way better thing. And you want low variability within each group, meaning that you want your data to be tight, not all over the place, but tight. And as you can see from last time with the t-test as well as this, when you have tight data down below, low score, and you have a higher numerator, then you're going to have a higher F or a T value or a Z value or whatever, right? And that's going to put you in the critical region where you want to go, passing that finish line, right? But in any case, I digress. Between group variance over within group variance. The between group variance is the sum of squares between, what's called the sum of squares between, I'll help you figure that out, and the degrees of freedom between, over the within group variance, which is the sum of squares within over the degrees of freedom within. And here we go. So now we're going to find the between group variance, and then we'll find the within group variance. And I'll just show you how to plug in those values very simply into the equation and to get your F ratio. So another term for the between group variance is the mean of squares between. And the way to find these values, or this value, is the sum of squares between over the degrees of freedom between. So I'm going to help you find both values very simply. The sum of squares between, I have a description right here of this formula. And remember, you're going to do it for each group. And I'll show you how to do that. So you're going to find the differences between the group means and the grand total mean for each group. So remember, we already found that. So for each group, you have the paper, the difference right here between the group mean of the paper versus the grand total mean. And then you have it for the standard electronic as well as the interactive electronic. And it looks like you have the best value here. You're going to take the difference of those and square them. Okay? And that gives you these values here. You're going to add up these values. And then you're going to finally multiply them by the sample size, which is 30. So 30 times 6.99 is 209.7 for the sum of squares between that top numerator value for the mean square between. Okay, so essentially find the difference between the group means and the grand total mean, right, for each group, then square them, then add those together, right, and then finally multiply by n, and that gives you that top value. And for the degrees of freedom between that below value, it's very simply a, where a is the number of groups, minus 1. So we have 2. So we take 209 divided by 2, right here, and you get 104.9 for the between group variance. That top value for our F ratio is 104.9. We're already halfway there, right? Oh, we're halfway there. Okay, that was bad. And here we go. Within group variance, also called the mean square within. Okay. And that's the sum of squares within over the degrees of freedom within. You need to be able to plug in values and find those two things, and then we'll find our value for our within group variance. Sum of squares within, this is the equation for that, and it's also basically the sum of squares of the group. And so you just basically add these three, since we were already given those, right, together, right here, and you get 203. Degrees of freedom within is the number of groups times the sample size minus 1. Okay? So you have right here, sample size is 30, minus 1 is 29. 3 times 29 is 87. So you have the degrees of freedom within is 87. 203 over 87, 2.33 for the mean square within, also known as the within group variance, and that's your bottom denominator value for your F ratio. Now it's just a simple matter of plugging in those two values, right? So the calculation of the F ratio is the mean square between over the mean square within, right? And those values are 104.9 and 2.33. 104.9 over 2.33 is 45.02, and that's our F value that we're going to compare to our F critical value to see if it passed the finish line and got in that critical region. So basically we've found our F value, which looks pretty large, right? Pretty huge, one would imagine, especially once you look at the table. But we need to look at the table to see, you know, what our F critical value is. So now I'm going to teach you basically how to find the F critical value on the F table, which is in Appendix D on page 355. I like to use that instead of the one in the book. The value the table they gave in the book in the chapter is not the same table as the one that they give at the end of the chapter. So it's like, that's kind of dumb. But anyway, I'm going to show you how to read this. And notice that you'll have right here your degrees of freedom numerator right here. And then your degrees of freedom denominator right here. And your degrees of freedom numerator, remember your degrees of freedom between, that's your numerator, is a minus 1, which is 2. So right here is where you're going to go. Okay? Just right there. And then your degrees of freedom within is a times n minus 1. And we figured out that value already, which is 87. And that's going to be in the denominator. So we're going to speed down there. And obviously, it doesn't show on this right here. Okay? I'm going to show you in the next slide. Your alpha level is 0.05. And they note that they give you two values. They give you the value for 0.05, which is non-bold. So those are the ones that we're going to look at, right? But the bold ones are 0.01, okay? But we're looking at the critical value, F critical value for 0.05, which is the non-bold. And we have enough information to figure all that out. So remember that our F critical value is going to be found by taking 87 and 2. So 87, 2 is going to be this column, remember, for the numerator. And then 87 is going to be the denominator of this column. I'm just showing you a little slice at the bottom of the table now. Okay. And notice that 87, they don't give you the value, so you really have to estimate it, right? And it's basically halfway between here and this value right here, almost, right? Essentially there. So remember, we're looking for the non-bold value, and the book says it's 3.11, and well, that makes sense, right? Because 3.11 and 3.07, it's essentially halfway between each other, right? So that's the value that we're going to give is 3.11. And does 45.02, our F value, exceed beyond 3.11? Of course it does, right? 4 does, 5 does, 6 does, and so on. You get it, right? So you just want to pass that value into the critical region. If you have trouble really figuring that part out, I like to graph it out and just kind of show where that critical region is, you know, 3.11, and then just start marching along and see if I can get past it. Then you want to make a decision, and in this case you want to reject the null hypothesis. That 45.07 or whatever it was is way beyond our F critical value of 3.11. So we're going to reject the null hypothesis. It makes our default action look extremely ridiculous, right? Reject it and conclude that there is at least one difference across the population means. But remember, we don't know which ones are different. Our F test, our Anova, just tells us that there is a difference. There is a main effect. The main effect is the test of differences between all the means for an independent variable. But we don't know which one is the main effect. We suspect which one it is, though, right? And so what we're going to want to do is use post hoc tests to determine, excuse me, where the main effect is and which group is most significantly different. And these are additional significance tests conducted to determine which means are significantly different for the main effect. In most cases, we want to control for the increase in alpha that will occur each time we conduct a pairwise t-test on the same set of data. And so there are different post hoc tests that they tell you about in the chapter. Some are more conservative and control for the tendency to make an increase in type 1 error when you do multiple tests. It's only appropriate to conduct post hoc tests, of course, if there's a significant main effect. So you run the Anova first, and then you do the post hoc after if you find a main effect. The most common type of post hoc test is called the Bonferroni test, also most conservative in adjusting for type 1 error. Just want to go over really quickly reading the outputs, the one way between subjects Anova in SPSS. I know I don't go over in these videos the how to do the SPSS because those are separate videos, which by the way is out, your SPSS assignment 2. Go for it. Super fun. But how do you read the output? So this gives you the output of the Anova. And it's pretty cool. So you can see the means differences and the total grand mean right there. Gives you your standard deviation, standard error. But the main thing that you're looking for here is this between groups right here. And notice your F score, 45.11, and your significant, which is 0.000. Remember, you can never have 0.000, so you report it as 0.001, for example, when you're reporting your results. Talks about that in the book. But you can see right here that that is lower, of course, than 0.05. So there is a significant main effect as this SPSS output shows. But it's not the post hoc test, so we don't know where the main effect lies. But of course, we can suspect where it lies as you look at the interactive electronic text of 7.833 is significantly very different than the standard electronic and the paper text. So the post hoc test you can run, and this is an example of the Bonferroni post hoc test. Post hoc tests indicate which pairs of means are significantly different from one another. And as you can see right here, the conclusion that you can make is the interactive electronic format is the most preferred. And how do you know that? Well, take a look at the box right here, interactive electronic text, and you're comparing that to the paper text as well as the standard electronic text. And as you can see, there's a much bigger mean difference between that, as we saw, right, when you just subtracted it and stuff, between that and the electronic text, and the significance is 0.000. And there's also a difference between the interactive electronic text and the standard electronic text, which is 0.000. So you can see the significant there. And these are plus values, which means that this is bigger, right, than those two. In the paper text, you have minus mean difference values, which means, paper text, not as good, right? If you look at the standard electronic text, you do not have significance with the electronic text. It's a minus value right here, but you do have significance between the standard electronic text and the paper text, as you can see right here. There is a mean difference of a positive value, and the significance is 0.01, which is bigger than or smaller than your p-value. And remember the test assumptions, similar to the independent samples t-test. Population of scores must be a normal distribution. The scores from different participants within each sample must be independent, and you also must pay heed to the homogeneity of variance. And that is the rest of the chapter on Anova. Hopefully it was helpful.